lecture of this course of sub-Riemannian diffusion. So we have seen how to build the sub-Riemannian Laplacian for a sub-Riemannian manifold using an external volume. So this was the formula, and you see that the volume is entering only in the first order terms and not in the second order one. And we have seen that the small time asymptotics of the heat kernel for this sub-Riemannian Laplacian can be put in correspondence with the sub-Riemannian distance. And this is, we saw that this is kind of independent on the choice of the volume, and it is kind of surprising, but this is how it's working. However, I would like to remark before starting to study something else. There are, of course, many other properties will depend on the choice of the volume. Indeed, the explicit expression of the solution will depend on the form of the volume, but also some qualitative properties that are very important. For instance, what is called the stochastic completeness of the manifold. So that means simply the following relation. So you say that your manifold with this diffusion operator is stochastically complete. So if the total heat, so we can compute just with the heat kernel, it is conserved. So this is the heat is the L1 norm. The total heat is the L1 norm of the solution of phi. So here I am writing just with the heat kernel. So I put a delta Dirac in a point. I make the evolution, and I am asking if the total heat it is conserved or not. So this is a property that is true in Rn, and also in Riemannian manifold. This is something that depends on the curvature. In particular, this property it is very sensible to the choice of the volume omega. So we don't have to forget that this independence on the volume it is for the small time asymptotic. So other properties are very sensible to the choice of the volume. So okay, but it would be nice to speak about stochastic completeness, but this is not our program. And so now I would like to finally, after that I promised for a long time, so I would like briefly to look for an intrinsic volume. So what does it mean, an intrinsic volume? So an intrinsic volume, it is a volume form omega that is built only from the sub-Riemannian structure. So if you want from not the choice of the orthonormal frame, so really our sub-Riemannian structure where we started from, or if you want it is equivalent, built from the manifold and the sub-Riemannian distance. So one would like to build an algorithm that, given a sub-Riemannian manifold without the choice of an orthonormal frame, will give you as a result a volume form. And we would like to know then what would happen. So if this volume form is a good volume form, it is regular, what we can do. Okay, so there are essentially two constructions. One, it is a differential construction. And the second one is a metric construction. This is the two kind of intrinsic volume that historically were built. Okay, so now I would like do something very simple today, and so see what are these two constructions and if they coincide or not. So we will start with the simplest case of a Riemannian manifold. So we start from Riemannian, then we go to study three-dimensional contact, and then I will give you some general results. So in Riemannian, what is the differential construction? It's simply what we do, what people in Riemannian geometry do everywhere, and so it is requiring that omega applied to an orthonormal frame F1 Fn is equal to 1. So this is an orthonormal frame. So this is definition of the Riemannian volume. It is it's called the differential construction, and this is independent on the choice of F1 Fn. To make a rotation, it gives you the same result. So that is the standard Riemannian volume. And so what is the metric construction? So the metric construction is to say, okay, M D is a metric space. So in Riemannian it is quite a standard metric space. So I consider the Hausdorff volume as N. And this is a way of measuring volumes. You can measure the volumes of an open set by using this Hausdorff volume. Okay, there is just a little difference. This built like this is a volume form. This is just a measure, but of course it is essentially the same things. And if you take any good book of measure theory, so you will find that omega is indeed proportional to Sn. You take, for instance, the book of Federer. So it is well known that in Riemannian geometry, the Riemannian volume coincides with the Hausdorff volume. Here I'm speaking to simplify about the space and Hausdorff volume. So, well, nothing else to say. So, in Riemannian there are no doubts about what is the volume that should be used. Either one or the other one, it is the same. This constant, of course, is not important, because if you change the volume by a constant, so in the sub-Riemannian Laplacian, really is not changing even for the constants. The constant simplifies, so this constant is completely not important. Okay, so that's obvious. So let's see now the next situation. That is the situation of a three-dimensional contact. So 3D contact. So in 3D contact we have, so I'll write it locally as M and a choice of two vector fields. Let's write like this, our manifold. And we have the span of x1, x2, and the bracket, x1 and x2, the dimension is equal to 3. Dimension of the span. So just with one bracket you get everything. And then, so what is the idea? So I'm speaking about the differential construction. the idea is the following. So, what can come to your mind? You say simply, okay, I have x1, x2, I have the bracket, and so I will define omega applied to x1, x2, and the bracket x1, x2 equal to 1. So one can say the following, but there is a difficulty that if we change orthonormal frame, so now I write a rotation of the orthonormal frame, so I do this small dimension, so it is easy to do explicitly. So I write cosinus of theta of x, x1 plus sinus of theta of x, x2 minus sinus of theta of x, x1 plus cosinus of theta of x, x2. So I make just a rotation of the orthonormal frame, dependent on the point, and then one compute easily what is the bracket between y1 and y2. So one would love that this bracket is equal to x1 and x2, but unfortunately it is not. So this is equal to x1, x2 plus, because you are going to make derivative also with respect to this x, because the bracket is making derivatives, and the fact that this depends on the point make this changing. So you get something that is not right explicitly, but a function f1 times x1 plus a function f2 times x2. So this formula is just some function. Okay? So what happened is that this claim, so that the bracket is not invariant. So if you change orthonormal frame, it changes. But so look carefully, because here you have something that is 1. And this is something that, so this part here is something that belongs to the distribution, so to the span over x1, x2. So what happened is that this is not invariant, but the bracket modulus the distribution, so this we call this D, okay, modulus the distribution X. And this permits to build the following. This permits to prove that this construction it is working. And so now, so what one can do, one do the following, and so one can say let omega 1, omega 2, and omega 3, the dual form to x1, x2, and x1, x2. So this, the tree form depends on the choice of the orthonormal frame. But now I would like to prove that indeed so indeed the wedge between these three forms is independent. So let's prove this very simply. So I would like to prove that omega 1 wedge omega 2 wedge omega 3 when applied to so I have the two frame x1, x2, x3 and y1, y2 and y3. So I would like to prove that this is omega 1 wedge omega 2 wedge omega 3. So this is the dual frame y1, y2, and y3. So I have to apply to prove that I want to prove that two forma are equal, and so I will apply to one choice of vector fields. It's enough one, and it is a free form, and so I will apply to y. So y1, y2, and y3. I want to prove the form. And this is by definition is equal to 1. So I want to prove that this form is equal to this. So this is the form of this is the dual of one frame and the other frame. And so when I apply to this choice y, I get the same. So if this is true, then the two forms will be equal. And so why it is so let's compute the omega 1 over y1. So omega 1 over y1, so omega 1 just is eating x1, so that cosines of theta. Omega 2 applied to y2, omega 1 applied to y2 give me minus sines of theta. And omega 3, omega 1 applied to y3. Y3 is written, sorry, of course, this is y3. Applied to y3, omega 1 applied to y3, get f1. Okay, and so now omega 2 applied to y1, you get sinus. Space, okay, the sinus of theta, omega 2 applied to y2, you get cosinus of theta, and then you get f2, and then omega 3. So omega 3 applied to y1 is equal to 0, omega 3 applied to y2 is equal to 0, and omega 3 applied to y3, so this is the fundamental thing, you get 1. Okay, so now let's compute this. So I have to apply this on this, this on this, and this on this, and so I will get cosinus of theta. Omega 2 is again cosinus, cosinus square of theta, and then omega 3 equal to 1, so I get cosinus square of theta, and then I have to make the first shift with minus, and so I get there is this minus, and so I get sinus square of theta, and all the others are equal to 0, because when I apply omega 3 or something else, I get 0, and so you get that this is equal to 1. Okay, so you see that in three-dimensional contact it is very easy, because you an intrinsic volume.
Ugo,
yes.
I think we simply put instead in this here, in omega here, and get the same result, equal to 1. Immediately, because this is omega is 3 form, then we get also 1. Not use this dual form.
Yeah, it is the same. Yes, yes. Maybe it was quicker. Yes. Yes, you define by this. You say you put inside. If you change, then you get the same. Yes, yes, yes. Of course, it was quicker to do like this. Okay. So well. Okay, so one would like. So this is very well. This is very good. But what to do when there are so in higher dimension? So in higher dimension situation it is a little more complicated, and I will not do the construction. And so in higher dimension, it is possible if the manifold is equiregular. And this is called the pop volume. But you have to be careful that you should imagine that when you are in higher dimensions, for instance, imagine that you have 4 vector fields in dimension 5. So you are in dimension 5 and you have x1, x2, x3, x4. And with one bracket you get everything. So now, so what to put here to define your form, you should make a kind of choice, because you have many choices of brackets. So you should take some kind of minimum along all possible brackets that you get. So construction is more complicated, but it can be done and provide you a good volume in any equiregular structure. And now, okay, so before saying this, I would like also to say the following, that I forgot, that in a three-dimensional compact, so one can prove that this pop volume, so this form omega that we built, is indeed proportional to the four-dimensional Hausdorff measure. So in three-dimensional contact, this volume form that we build in this way, it is, as in the Riemannian case, it is proportional to the Hausdorff measure. So be careful that here you have to put you should put the right Hausdorff dimension to measure volumes. So you have the impression that this will work very well in general. So you have this differential construction that you can generalize in the case of pop, and you would expect that a formula like this, it is always true. Indeed, it is not the case, and we have the following lemma that I'm not going to prove, that will require 4 or 5 lectures alone, that says the following. So let mu a smooth volume. So if we have an equiregular structure, then we have the following. So the pop volume, so now I call it P, so it was that omega, pop in general. So the pop volume is a smooth, so I will write it like this. So this is just a smooth function. Is the Radon-Nicolin derivative of the pop volume with respect to mu. So this formula just says that the pop volume, it is a smooth volume. And then you have that SQ, so the spherical Hausdorff volume, that we write as F of S mu. So I'm simply taking a reference volume mu, and I'm going to see if, so how you write at the pop and the spherical one with respect to mu. So you have that, so if we write this, you have the following, that, so as I said, f p mu is infinity, f p mu is equal to f of s mu if n is less or equal than 4, and the dimension of the manifold, and if n is bigger or equal than 5, then you have that f, the two are different. Mu is different from f mu, of course, in general. And last and most important thing is that f s mu is this one is C0, so you can prove that it's C0, but there are examples. I will write, but maybe I will write here otherwise. It's not possible to see. Okay, so there is this example where we have that this f s mu is, I will write like this, is C3, but not C5. So situation from the point of view of measured field is very, very complicated. So what I claim here is that so the pop volume is always smooth, and the spherical Hausdorff measure with the right dimension, in general it is not smooth, it is just C0. So what is possible to prove is that it is C0. Probably it is a little more. In dimension less or equal than 4, the two objects are proportional. Of course, equal, I mean here, I mean proportion, But in dimension bigger or equal than 5, the two are different, and you can prove that the spherical Hausdorff volume is not smooth. So that is very complicated stuff. And so this means that in sub-Riemannian geometry, so in sub-Riemannian, starting from dimension 5, from dimension 5, so there exists more than one intrinsic volume. Indeed, there exists two, and so there exists infinity you can take in combination of the two.
Are those functions at least bounded with respect to each other?
Yeah. Of course, it is. What is known is that they are commensurable, so that you can find a function bounded. So they are. You can find a function that is less than infinity and less than and bigger than 0 uniformly, such that they are. But this is, you see, it is complicated, because if you would like to build an intrinsic Laplacian, you don't know what to choose. Here it is, and some properties will depend on this. So there is a.
Yes. But if you take f sigma mu, I mean for prop, it would be C infinity or not?
F.
I mean
F P mu.
Yes, dimension more than 5, more than 1. Whereas this would be smooth or not? So you say that
No, this is always smooth. This is always smooth.
oh, okay.
This is always smooth. The pop volume is always smooth. What is not smooth is out of this. It's always smooth.
In the dimension less than 5, it is uniquely defined.
In dimension less, in dimension less than 4, it is in yes. Less or equal than 4, yes. Dimension less than 5, it is intrinsically defined. So it is the same. The two volumes are the same. And so this is just said in one word. This is due to the fact that this, so if you want to relate, if you want to write P as some random Nikodym derivative with respect to the spherical of S, Q, then you can prove that this function here, it is the volume is proportional to the volume of the balls of the nilpotent approximation. Because when you build this Hausdorff, you just need very small balls, and so what will be important at the end is the volume of ball. So this is essentially the volume of balls of nilpotent approximation. And the fact is that the nilpotent approximation is something that in dimension less or equal than 4 is constant, in the sense that it's not depending on the point. So if you compute an nilpotent approximation on a point, you get always the same structure, like a Riemannian. You compute an nilpotent approximation of a Riemannian structure. So you make a blow up of the structure, you get a Euclidean structure. In any point is the same. But starting from dimension 5, the nilpotent approximation depends on the point, because there are some parameters that come out. And so, because of this, this will depends on the point. And since it is the volume, so this volume will depend on how the sphere is done. And the sphere is not, even if the structure is changing smoothly with the point, the shape of the sphere will not change smoothly, in the sense that it will be cut locus that creating. So it's a very long story, but maybe I can discuss later on this after if you're interested about this topic. Okay.
Excuse me, one more. So it seems that if this sub-Riemannian manifold is homogeneous, then this one function would be the constant, yes?
Yeah. Only groups. Only groups. Yes. Only groups. They are the same. Only groups. These are both left divided. So P is proportional to SQ, that is proportional to the hard. To the hard nature, of course. That's good remark. Okay, so now I would like okay. So now some examples of this construction. But now, as you see, everything was work already quite strange in the equiregular case, and so it is interesting to ask what happened in the non-equiregular case. Now we need some different example of computing this. So we start with the simplest case. This is the Heisenberg case. So in the Heisenberg case, 1, 0 minus y over 2 and 0, 1 x over 2. So you want that your pop measure, so you compute the bracket. The bracket between the two is 0, 0, 1. So you want that your pop measure, when applied to this and this, give 1, and you immediately get that P is equal to X, Uy, and this. So this is equal to the Lebesgue, the standard Lebesgue volume form in this coordinate. And so, thanks to this, so the sub-Riemannian Laplacian, So this we computed already yesterday. So this is the standard LabX. So these two vector fields are divergence free. So the sub-Riemannian Laplacian will be f1 square plus f2 square plus the other two terms, divergence of f1 times f1, divergence of f2 times f2 will be just 0. So what we did yesterday for the Higgs kernel was indeed done for this intrinsic Laplacian with intrinsic volume. But that is because of the case very simple. Okay, so now let's do something more interesting. Let's see what can we say in a non-irregular case. So I would like to study briefly the Martinez structure. So the Martinez structure, it is we are again in R3, and the two vector fields are 1, 0, y squared over 2, and 0, 1, 0. Okay, so we compute the bracket between the two. So I have to compute so differential of this times this is 0, differential of this times this, and so you get so minus. So this is making derivative with respect to y, and so you get 0, 0, 1. And so you see that this structure is not equiregular, because if you compute the span, so as we did, we called D1 the distribution, so the span of these two vector fields, and then D2 is the span of the first, the second, and the bracket 0, 0, minus y, and so this has dimension 3 if y is different from 0, and has dimension 2 if y is equal to 0. And so to get the full dimension of the space, you need to go in the delta 3.
Free if y is not 0.
Sorry?
Free if y is not 0.
If y is different from 0. Okay. And so you should compute one more bracket, and so if you compute the dimension of D3, you finally get 3. So this is not equiregular, so the number of brackets that you need to get the full dimension of the space depends on the point. So how to build a volume? How to build a volume? So, okay, we can build, so we can take the pop volume on, so on this, on let's say y is different from 0, and if you do this, you get that the pop volume P on y different from 0, this is contact. For y different from 0, this is contact. It's the dimension of contact, so we can use the construction that we did. And if you compute this, so essentially you have to so you put in a matrix 1, 0, y squared over 2, 0, 1, 0, and 0, 0, minus y, and to compute this form you have to compute the inverse of this matrix, and then this will give you the tree form, and then you make the wedge. So this is a very simple computation, and you get that this top volume is minus 1 over y dx wedge dy wedge dz. So you get something that is this is not integrable. Okay. So now the question is possible to regularize this? So one could think to find some algorithm to so you have a volume that is singular. One can try to get this singularity with some other construction, like kind of quotient. But this is not known how to do. This is really not known. Of course, for the specific example, you can regularize, multiply by y, and it's done. But I mean, if you take a general structure and you build the volume this way, so you will get a form that is diverging somewhere, and it is absolutely not known how to regularize, and it is essentially believed, even if this is not really something that can be stated mathematically, it is believed that it is not possible. It is even not make sense to try to extract a regular volume from a non-equiregular structure. Because you see, this is contact out of y. So we still have that P, it is proportional to Hausdorff on y different from 0. So both construction of Pop, so the metric construction, differential construction give you exactly the same result. Everything is diverging and there is no way of regularizing. And you find a way of a nice construction of regularizing this volume. I would be interested, but it is not nobody know how to do. And so now, okay, we say we have a volume like this, so let's try to build the Laplacian in any case. So now I would like to build this sub-Riemannian Laplacian with this diverging volume. So I have to compute the divergence of the vector fields. I have to compute. So this is equal to f1 squared plus f2 squared plus the divergence of omega of f1 times f1 plus the divergence of omega of f2 times f2. So this is regular, there is no volume inside here, so we have to compute this. So the volume has the form of minus 1 over y, so x dy dz. So the divergence with respect to omega of f1 should compute 1 over this function, 1 over h, and then I should compute di, so I should put again the function 1 over y, and then so f1 component I, so let's compute this, so minus and minus go away and get plus h, and then I get dx.
And what is h?
1 over y and 1 over y. So, thank you very much. Y. So the x 1 over y, and the first component of this. So you get this plus dy 1 over y, and then the second component is 0, plus dz, and then again 1 over y, and then y squared divided by 2, and this is equal to 0, so great. And if you compute the second one, so I will not repeat this computation, so the divergence of omega of f2. So you understand that when you use the second one, you will get something when you make a derivative with respect to y of 1 over y, here multiplied by 1. And at the end you get this is equal to this divergence of is equal to minus 1 over y. Okay, so how much is this? So this Laplacian will be dx plus y squared divided by 2 dz applied twice plus dy applied twice, and then I have one of these terms, that is 1 over y, 1 over y times f2 dy. Yes. Is correct or? Here I'm using the divergence of one is computed with respect to this pose. So how to compute this? So the divergence of a vector field f is equal to 1 over h, and then di h fi. And h is what you have here. So this is the divergence with respect to this volume.
Yes, I'm just wondering whether the expression in the bracket is indeed equal to 0.
The bracket?
No,
The second item.
the second item.
The second line here. Because this is multi. So I have to make dx the volume times this, so this is 0. The second one is dy minus 1 over y, and then I should multiply by the component, which is 0.
Okay. Okay, there is 0.
Here there is 0. Multiply by the component. It will not be 0 second time. Second time is this term that has 1 there. And so get minus 1 over y. Okay. So great. So you see that now this Laplacian, that it is the most reasonable Laplacian that you can build on the Martinet surface. So has a term of first order that is diverging. So now we cannot say that these first order terms are not, because this is not anymore hyperelliptic. So in y equal to 0, all theorems that we have discussed up to now are not working anymore because they were for some they were true for operators with infinity coefficient. And indeed, we have the following. We can prove the following very interesting lemma, that this delta sub-Riemannian is essentially self-adjoint in R times R plus times R. So what does it mean? It is that in this so here I have x, y, and z. So this acts. So this is the, let's say, what is called the Martinet surface. So this plane here is separating the space in two parts. So the part on the right and the part on the left. And this lemma says to you that this sub-Riemannian Laplacian is essentially self-adjoint only on one side. And so this means that the evolution will stay, all the evolution will, if you start with an initial condition on one side, all the evolution will stay on that side. So this means that the heat, is not crossing the singularity. So this is a very interesting phenomenon. So the fact that is so this singularity makes the volume going to infinity here, and this behaves like a barrier, because the fact that the Laplacian is essentially self-adjoint on this side means that if you start with the initial condition here, so the evolution is always on this side. Of course, it is essentially self-adjoint on the other side, and is also essentially self-adjoint on the two sides together. But the fact that it is essentially self-adjoint on one side means that the two parts are not communicating. It's like when you study. So imagine that you study the heat evolution on the line. So so the Laplacian on the line is self-adjoint on the full line, but it's not self-adjoint on half line. Because if you take half line, you should give some boundary condition. So this means that you can consider the evolution of the heat only on one side. But if you have the Laplacian on one line and another line, you consider that your manifold is disconnected. So the two parts are not. So the Laplacian will be self-adjoint on this side and on this side. So the two parts are not communicating one with the other one. So nothing can be sent from here to here. And this is exactly the situation. So this barrier is a complete, since the Laplacian is self-adjoint on one side, does not permit anything to go on the other side. Because the evolution equation will work on this side. So we start with some initial condition there, and we stay there. And so this is an interesting phenomenon. And in particular, so in this example, you should notice a connection with another things that I was telling you yesterday. This is an example of a situation in which you have of a manifold that is not complete, and the delta self-adjoint. So you remember that M complete implies delta self-adjoint. So this is triggered theorem. And so this example is an example in which you show that the opposite is not true. So you can have indeed the Laplace that is self-adjoint and the manifold that is not complete. So why the manifold is not complete? Because geodesic are going on the other side. So with this vector, with the vector field, with this one, so you cross this set. So geodesic are going through this singular set. They don't see any singularity. So this is a counterexample to the opposite. To counterexample to this to the opposite implication of the string theorem. So, and final remark, then we make a stop, and then I will briefly say you something about random walk. And I wanted just to tell you, yes, that on this, so all theorems that we saw yesterday are wrong on this Martinet structure. So, for instance, yesterday we saw, just to make an example, that PT of x, y, so the log of PT of x, y tends to the distance square between x and y divided by 4t. So this is now is not true. Because in this Martinet surface, so in this Martinet case, the distance between 2 points on one side and the other side is finite. So this is finite, but the heat kernel, if you build on one side, will be 0 on the other side. So there is no communication. So this is wrong. This is wrong due since so this is since omega, so the volume explodes. Since the volume, the top volume explodes. So yesterday I said that the heat kernel is related to the distance for small time very, very strongly. If you consider a smooth volume, so consider the right volume, the right intrinsic volume for this non-equiregular, then these kind of theorems are not holding anymore. And same on Gaussian, so you can do by yourself. So on Gaussian, it's very similar. In that case, we have just the Riemannian volume. Okay, so we see in 5 minutes. To very briefly we have studied the diffusion from a macroscopic viewpoint, so thinking the heat as a fluid, so we compute the divergence of the gradient and so on. Now I would like to give a very brief introduction, let's say almost nothing, but at least to show you that you can really interpret the diffusion as a limit of some random walk. And so to do this, I will do in the simplest case. So I would like to explain you the Stratonovich approach. So what is usually called the Stratonovich approach. So we take Riemannian, or sub-Riemannian manifold, and so I'm just thinking to something like so a choice of vector field Fi, from 1 to n, so it could be Riemannian or sub-Riemannian, it doesn't matter. And so here f1 fm is fixed. So I'm really considering some random walk that will depend at the end on the choice of this orthonormal frame. So now, so phi is a density or probability of finding your particle somewhere. And we are going to reason like this. So just making a Riemannian picture. So these are the integral curve of f1, for instance. This is the integral curve of f2. So what I will do, I will start from a point q, and consider a particle that is here at time t, and then I will make this particle jumping on the integral curve of the vector field. So, and could jump here, 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 or here, in these 4 points. And so I'm jumping, in time t, delta t, let's say, over epsilon. So here I have to say I jump in time delta t of some quantity epsilon. So this is, let's say, this evolution of epsilon along the integral curve of f1. And now I would like to write an equation for the density of probability. So I will do something very, very simple. So I will say that the difference between how much is q in time t plus delta t minus phi of q at time t. So phi is a density of probability, or if you think to a lot of particles, it's just a number of particles. So how much is going down here, so I mean one step delta t, and so how much, sorry, is going up here. So I take it equal to the average of how much is phi in this point. Because I think there are a lot of particles moving back and forth. So if how much you have here is equal to the average that you have in these 4 points, nothing will happen. The same number of particles will go, the same number will come back, and the difference will not change. But if here I have more particles than here, then this will move. And so I will take, so this is 1 over 2m. I will do the following. So the sum for m from 1 to m of, I will explain this formula. This is very, very simple. So phi on the integral curve of fi of q times t plus, so I should go back, phi of pi epsilon q in time t. And then, okay, in this q time t, minus phi of q t. So pi is the flow, so pi epsilon is the flow of fi. So what I'm just saying here, so this is precisely the average of the difference between the value of the function and the average that you have in the points, because I take this point, so I evolve with the first vector field for positive time, and then I evolve for negative epsilon there. So I go here, I go here, and then with the other vector field. And then I subtract the value of the function here. So this is the average. This is the average. thinking that I'm computing the average of these 4 points. So I should start from here, and then in the picture m is equal to 2, so I have this point, that is this one, this point on the back, that when I make evolution is the other time, and then I take the other vector field, and I have this point and this point. So I'm claiming that how much phi is increasing in this point is proportional, then I put proportionality equal to 1 to the difference between the average that I have in this point and what I have here. If this average is equal to what I have here, so if this is equal to this, so there is no difference, because I'm in equilibrium. Everything is the same, and otherwise I get this. Okay, so now I divide by delta t, and I get that phi over q t plus delta t. So later on we are going to make a connection between these two. Minus phi of qt divided by delta t. I want to make appearing the derivative with respect to t. So I'm dividing, so 1 over delta t, and then this 1 over 2n, this sum, this term I'm not copying again, minus phi of qt. And this is of course like this. Okay. So now I would like kind of showing that this will send for the delta t going to 0 to the Laplacian, to some kind of Laplacian, and then we have to make Taylor expansion. So I would like to make Taylor expansion of so we have to make Taylor expansion of each of the terms, so of t over pi epsilon of q. Okay, so how to make a Taylor expansion in epsilon? So this is so I have a function, I have a point, I make evolution with the vector field fi, and I would like to compute the Taylor expansion with respect to the time in epsilon. So simply we have to compute, so the term, everything is moved here, the term of order 0, we have to take phi of the flow in time 0 is the point, so I get phi of q. The term of order 1, I should take the derivative with respect to epsilon, in epsilon equal to 0, of the function of phi of pi epsilon of q. Yes, this derivative, and then I should multiply for epsilon. This is the term of order 1. So what is this derivative? So I have the differential of phi, and then I should compute it on the derivative of this. But how much is d over d epsilon pi epsilon? So this is the vector field fi, by definition of flow, computed in the same point, so in p epsilon I of q. And so I get d phi computed at this point, fi of p epsilon I of q, computed in epsilon equal to 0 times epsilon But we are done because now this is again for epsilon equal to 0, this is again q. And so this first term is the differential dphi applied to fi times epsilon. And so this is equal to, by definition, fi applied to phi as operator on function times epsilon. So this first order term is your vector field applied to the function times epsilon. So now let's take the second order term. So we don't make again the computation, it's the same computation. Second order, the term 2. That's very nice because the second term is you get 1 over 2 factorial, of course. Then you have to apply twice this operation, twice this, and then you get the vector field fi applied twice phi times epsilon squared. Great. So you see, arriving these terms there. And so now I have to compute so now I have to put all in this formula, this expansion in epsilon, and what I have. So maybe I should write it again what it was here. Plus the one minus epsilon, right, like this. Just copy that form. And so what we get as an expansion. So I get 1 over delta t. Then I have 1 over 2m, the sum from 1 to m. So now we have the term of order 0. So term of order 0 just disappear because the term of order 0 is phi of q for each of these terms, and I have phi of q, and I have 2m of this. So the term of order 0 are just 0, because I have this term here. Each of these will provide the same phi of q. So this term of order 0 will be phi of q. This will be also phi of q. And how many I have? 2m. So I will just simplify everything, and so this I get 0. Then I have the term of order 1. Term of order 1, we have to use this formula here. So term of order 1 are of the kind fi of phi times epsilon, and then this one, this is minus epsilon. So I get fi of phi, it becomes sinus minus, because epsilon is now this same computation was minus epsilon. And so this first order term is also 0 by symmetricity. Then I have second order term. Second order term are that one, and so I get plus 1 over 2 factorial, 2 is 2, and then I have twice the term. Now I have the same sign. And so I get fi square applied twice to phi epsilon square. So great. So at the end, this will be equal. That's great because what we get it is 1 over delta t, and then you get 1 over 2m. 1 over 2m is a constant, we don't care too much now. I get a constant c, and then the sum of the square of q fi applied to phi, applied twice to phi times epsilon squared. Okay. So great formula. Because now we would like to relate delta t to epsilon. So I recall that what we are doing, because in this picture, because to say, I start from here, I jump in, so I have a step. Indeed, in this computation, just the second order terms appear. So 0 order, we wait for this average. First order term go away by symmetricity, and then you see just the second one. So
and then also higher order terms.
yeah, of course, sorry. And then I have, plus a big O of epsilon cube. So thank you very much. Yes. There's some big O of epsilon cube. So now what I'm doing, in time delta t, I jump here of epsilon, and I would like to relate epsilon to delta t. So what happens if I take delta t equal to epsilon? So this would be the most natural choice. You see that this is not working, because if I take delta t equal to epsilon, so here I have epsilon, or if you want delta t, and then you get in the limit, if you make the limit, you get that dt phi, the equation that you will get is equal to 0 due to this square here. So I will not make this choice. And so we make the choice delta t equal to epsilon square. So this means that the velocity of propagation. Essentially what I'm doing it is when I refine this, I send epsilon smaller, so the velocity will increase. So the velocity that is epsilon divided by delta t, so become epsilon divided by epsilon square. So velocity space divided by time, and so this is 1 over epsilon and 10 to infinity. Okay, so this means that when you go very small, at each step you move always more quickly. And this is so you always read on all books that velocity of propagation. Propagation of heat is infinite. This is related to this fact. You should assume that your particle is going very quick, otherwise you have no diffusion. And so now we make the limit for delta t for epsilon going to 0, and what we get, the equation dt phi equal to a constant, and then I have the sum of fi squared of and so this is you see it is a heat equation where we see appearing only this second order term of the Laplace. And this is frame dependent. So this is frame dependent. this is frame dependent, and also there is no use of volume. So what I did, I have not used any notion of volume. So it is also hard now for this operator to study self-adjointness, because self-adjointness is first symmetricity with respect to certain volume. So that is not completely a good operator. This is how you get this great sum of square that was used it was used a lot, starting from the 60s by your mother that was studying this evolution, because they were starting from some vector fields and studying this diffusion. They were studying stochastic stuff, but this is the way in which you see in a deterministic sense the stochastic differential equation. So, okay, now I will just give me 5 minutes more and I will finish. So how to get in Riemannian, so the Laplace Beltrami. And then I will tell you that in sub-Riemannian we still don't know how to do, but at least in Riemannian. So in Riemannian, how you get the other terms? So how you have to reason to get the true Laplacian. So again, it would like to get sum of plus divergence of omega fi, fi. So how you get the right operator in Riemannian? So Riemannian should do like this, and not to make a computation because my time is finished, that one can do the following. Instead of taking the two vector fields like this, so the vector fields of the orthonormal frame, you don't fix any orthonormal frame, and you take the sphere of radius epsilon. And so you jump on the sphere with a kind of uniform probability. So here we are jumping just on the end point of the integral curves of the trajectories. Here instead I'm jumping really on the sphere, and so I do as before, so phi of q t plus delta t, again I jump of epsilon in delta t, minus phi of q t equal to, so now we make an average on the sphere, so on theta belonging to Sn minus 1, so I parameterize with my initial velocity that will belong on a sphere of so endpoint of geodesics, so this is the exponential map, if you want to can write like this. So the endpoint of geodesic starting from the point Q with a direction theta and for time epsilon. And then I will subtract, so I should make some measure here, the theta, and minus phi of qt. So here I'm just doing exactly as before, but instead of making average on the 4 points or 2m points, here I make average on the full sphere, and I should put some uniform measure on the direction. So this is a uniform measure on direction. This is, we have this because we have the Riemannian structure, we are in Riemannian, and so I have a Riemannian structure on the tangent space, so the direction belongs to the tangent space, so this is Euclidean space, and I know what does it mean being uniform with respect to the direction. So this implies that, so I have this one by the Riemannian structure. And so now you can do the same computation as before, so we have to make an expansion of this with respect to epsilon, and then you get that you take again epsilon equal to delta t squared, so you have to make again this scaling, and then what you get is that the limit, only second order terms are important, and you get that dt phi is equal to, you get a constant, and then you get really our right Laplacian, some square plus the divergence with respect to the Riemannian volume of Fi. So in Riemannian, the microscopic approach, this microscopic approach this second one on sphere, let's say this on sphere, coincide with the macroscopic approach. So you get, thinking like this, you get precisely the right operator that you like. So my lecture are finished, and so I will conclude with
Ugo, excuse me.
Yes.
It was previously opposite. Delta t is equal epsilon squared. In previous.
Epsilon equal to the delta t square, but
Yes, it was previously.
Yeah. Otherwise it's not working. Thank you very much. Otherwise not. Yeah, the velocity should go to infinity. Otherwise it will not work. Yes, thank you. So now you understand what one would like to do. So since in sub-Riemannian, in sub-Riemannian, the macroscopic approach give a non-unique diffusion, because the volume is not unique. At least starting from dimension 5. And what about, so is it possible to build to make a microscopic approach in sub-Riemannian? And that is a big open question. The big problem is that here you have a uniform measure on on the direction that is well defined. While in sub-Riemannian, geodesics are parameterized on a non-compact space, so on a cylinder. And you don't have a measure on this cylinder to. You can do the same. You can take the exponential map and measure, and then use some kind of uniform measure on the different geodesics. But in sub-Riemannian geometry, we don't have on this cylinder of initial condition a measure to say what is the difference. So how much weight give to a geodesic to another one. So this is the big problem. For several reasons, because the structure is not enough. So we don't have enough structure. So now this is a hot research topic in this period. So there are different groups trying different approaches, and then the situation is anyway complicated. So this is the frontier of research what people is doing now on the subject. But you see that in Riemannian everything is working well. So you have this macroscopic approach, this microscopic approach that you can render completely invariant and get the right operator. So if you fix an orthonormal frame, you get sum of square both in Riemannian or in sub-Riemannian, and that is also working well, but you don't get the intrinsic Laplacian, so your Laplacian has nothing intrinsic. And in sub-Riemannian, building a kind of approach like this, that one would like to see if with a microscopic approach one could kind of select between this non-unique Laplacian that you get with a macroscopic approach, the most natural one. But that's not
microscopic approach is sometimes more convenient. Why is it important to understand?
Because the macroscopic approach is kind of understanding from stochastic viewpoint. So the heat is describing in particular this limit of this random walk, where of course I cannot prove here that so I just got the equation pointwise. So of course there is one would need to prove that really the solution converges. So of course here there is something that here I just proved that pointwise the equation is that one. So I have not proved that the solution of the random walk converge to the solution of the heat equation. But this is the case anyway. And there. In diffusion, so the two approaches are analysis and stochastic, were always kind of two different viewpoints that permitted to some of the results were obtained with one approach and some other with the other approach. So very often, if you can get one result with one approach, you don't get with the other one. For instance, all results of the end of 80s and the beginning of 90s of Leandre, Benarus, and so on were always